Yeah, good morning. In the last class, we discussed about the angle of departure, and today we discuss about the angle of arrival. So, when we are going to calculate this angle of arrival is when there is complex zero in the when there is complex zero in the Locus transfer function. Suppose if the complex zero is present, then we are going to find out the angle of arrival. So you see how we are going to calculate the angle of arrival. Pi a is equal to, we have the equation that 180 plus pi. Whereas in the angle of departure, we have taken 180 minus pi. In the angle of departure, we have calculated 180 minus pi. So angle of arrival is 180 plus pi. So that is only the difference, and the remaining methodology is same for calculation of this angle of arrival. So the pi is also similar to that, summation of pi p minus summation of pi z. So we know how to calculate the pi p and pi z. Okay. So there is, suppose assuming that there is a complex zero. Zero is represented with the small circle. Say for example, this is a complex zero at say -1 and say -2. This is say -1.5. So if I have, this is a complex, so consider complex zero. Any one of the complex zero is considered while calculating the angle of arrival. So then represent if you have any poles, or say for example it is 0. At 0 we have one more pole, and say for example here I have 0 at -3, and -4 I have one more 0, say for example. So then how to calculate this angle of arrival? In the sense, we need to join all this to the considered complex zero. So this is one which you have considered. So then this is the one we have joined. This is angle made by pole 1. So there are two poles and two zeros. So pi p1 I can say, and this is 0. So which is called as pi z1. And this is, if I join to here, then I'll be getting pi p2, and this one is going to be pi z2, and this one is going to be pi z3. So these are the angle made by each and every pole or zero present in the given Locus transfer function. So this is a real axis and then imaginary axis, assuming that. So we need to find out this pi p, means say for example pi p1. In this case pi p2, there are only two poles, and minus of pi z1, pi z2, pi z2, then pi z3. So these are the three angles made by the three zeros, and these are the angles made by the two poles. So we are going to calculate this pi. We are going to calculate this pi. After calculating this pi, then we are going to use the equation pi a. Pi a is equal to 180 plus pi. So by using this, I'm going to find out the angle of arrival. So in the similar what we have done in the previous case, similar to that we need to do. So these are the steps these are the rules which you are going to say in construction of root locus. Now, so just I'll brush up what are the steps, what are the rules which you need to follow in construction of root locus. So we know that one is first we need to draw, say for example information about, we need to get information about, those are the rules which you need to use. Okay, get information about the poles, I mean number of open loop poles and open loop zeros. Either it may be a complex or real. It may be a real or complex, whatever it is. First, you need to find out the how many are there. That is, we are calculating the p and we are calculating the z, how many are there, and also locations, not only the number and also locations. Means, say for example, s is equal to -1 or -2 somewhere. So that is what we can say location. So number, say how many are there, and the locations of those also to be found. I mean, get the information about those. Get the information about this is the first thing. Then we need to plot pole zero plot. We can say plot of pole zero means we need to draw initial. Say for example, as I told that once you find out the locations, so at which point these are the poles or zeros, whatever it is, where it is lying on the real axis or imaginary axis or in the space. So this is we need to find out. I mean the pole. I mean we need to plot the initial. We can say it is called initial root locus. We can say it is called as initial root locus, and this is a plot of pole zero which we have discussed in the rule 3. Okay, rule 3. So this is about the rule 2 and this is about the rule 3. Means we need to find out the plot of pole zero and then identify sections. Sections of root locus. That is what we are going to do in the rule 3. Then finally, next is going to be calculation of angle of asymptotes, and location of asymptotes. So this is the thing which you need to find out. This is, of course, as I told, that it depends on the rule 4 is depends on say rule 2. If p is possible cases, p is greater than z or p is less than z or p is equal to z. Only in the first two possible cases, fourth one will be taken. That is, fourth step is taken as. Next, fifth one is breakaway points. We need to find out the breakaway points. Then the sixth one is we need to find out the intersection with imaginary axis. So intersection with imaginary axis. Then seventh one also we can find out the angle of departure and angle of arrivals. So these only this will be used only if there is complex pole or complex zeros present in the open loop transfer function. Then only this can be used. That is pi d or pi a or pi d and pi a. You can both may not be exist, may exist or may not exist, because in the numerator and denominator, if you have the complex roots, then we can say we have to use the both. If the denominator only if you are having, then we can use the only pi d. If the numerator is having, then we can use the pi a. So this step is also depends. So rule 7 or step 7, the step 7 is also depends, and the step 4 is also depends. These are the remaining all are same. That is 1, 2, 3, and then 5, 6 has to be used for all the sums. So these are the steps which we can say, and we'll take one example. When we take example, and if possible use the graphs. For construction of the root locus. So I'll take one example. So draw the approximate root locus diagram. Draw the approximate root locus diagram for a closed loop system. Whose loop transfer function, whose open loop transfer function is given by say g of s into h of s is equal to k by s into s plus 5 into s plus 10. Okay. So here k is the system gain, that is called as a constant. Okay, system gain constant. Right. So now, as I told that the first step is you need to find out how many poles are zeros are there. If we see in the numerator, there is no value in the s, so there is no. It is a simply only denominator. We have the values of s, values of s. In the numerator, we don't have any values. It means here it doesn't contain any zeros in the system. No zeros in the system. So we can say no zeros in the system because the numerator we don't have any s values. No zeros in the system. Then we can go with poles. We can go with poles. How many poles are here? See, there is 1, and this is 2, and this is 3. So there are 3 poles. There are 3 poles in the system. And how many zeros are there? Number of zeros is z. So P is greater than z. So P is greater than z. So that is what the initially we can find out. And the number we have found out, the locations also we have to find out. So locations in the sense at s is equal to 0, and at s equal to -5, and at s equal to -2. So these are the open loop pole locations. We can say starting points of, these are called starting points of root locus. Starting points of branches of root locus, I can say branches of root locus or starting points of root locus. Okay, so once you find out this 0 and 5, and these are all because there is no 0 to approach these poles, all these 3 poles will be approaching to infinity because p minus z number of poles, p minus z, that is 3 minus 0, that is equal to 3 poles approaches to infinity. Approaches to infinity, assuming that there is a 0 at infinite location, and assuming that there is a infinite, because we told that the root locus starts from the pole location and ends at 0 location. As there are no zeros in the system, we can assume that there is a 0 at infinite location. So all these poles are starting points of the root locus, are starting point of the branches of root locus, will approaches to infinite, approaches to infinity. So 3 different direction it approaches. So because three poles are there, each pole will approaches to infinity. So 3 directions are required. 3 directions are required for the approaching the infinity. Right. So now once you find out that, the next is going to be we have to find out the sections of parts of root locus, right? So that is the step which you have to find out. So for that we need to draw. For that we need to draw a, right. So this is one which you have drawn. Initially, you need to take the what you call graph. Use the graph for plotting this root locus. Plotting this root locus, we need to use the graph. So real axis is here, and real axis, and this is going to be imaginary axis. So here this is a 1, and this is a 1, 2, -1 and -2, say -3, then -4. We have up to 10, right? So uniform -6, -7, -8, so -9, then -10. So now we have found out this pole 0 plot. I have drawn the s-plane. I have drawn the s-plane, and I need to identify which part. Before that, I am going to locate all these poles which are at 0. We have 1 pole. At 0, we have 1 pole, and at -5, we have 1 pole, open loop pole, and at -10, we have 1 more pole. At -10, we have 1 more pole, right? So now if you look at the sections of root locus, only we have from here to here, means this is one section. From here to here is one section. From here to here is one section, and till infinity is one section. So I have 3 sections, 1, 2, 3 sections. So identifying these 3 sections, from this pole to this pole, So if you take any point between this section, so right side if you count, left side if you count, so count should be odd. Count should be odd. Count of poles and zeros. If a count is odd, then this between section, complete section. So from here to here is a part of root locus. It's a part of root locus. So that has to be made thick. That has to be made thick. Similarly, if you take the second section, anywhere between this section, you take any point and count onto the right side of this point. If we count, the count is going to be even in this case because there are two poles here. So this between say these two, that is second section, is not part of a root locus because count is even. And see, if you take this third section, that is between the pole and the infinity, between the pole, third pole and infinity. So if you take any point on this, if you count the right side of that, here I'll be getting 1, and here is 1, and then here is 2, and then 3. So count is odd. So this shows the part of root locus. This shows the part of root locus. So this is what we can call it as initial root locus or whole zero plot. Also we can say whole zero plot. So this is what we have done, whole zero plot. Next step is, that is the third step is over now. Then fourth is angle of asymptotes, and fifth is location of asymptotes, right? So here this fourth and fifth is depends on the possible case. As it is p is greater than z, we have to go for the 4 and 5. So now finding the angle of asymptotes. So how to find out the angle of asymptotes? We have given the equation, that is theta is equal to 2q plus 1 into 180 degrees divided by p minus z, and where q is 0, 1, 2, because it is still p minus z minus 1. So 3 minus 0 minus 1 is 2. 3 minus 0 minus 1 is 2. So that's why I can end up at 2. So now theta 1 for q is equal to 0. For q is equal to 0, p minus z is 3. So 60 degrees I am going to get. Substitute the q is 0 and p is equal to 3, and then z is equal to 0. Then I am going to get for 0 it is 180 by 3. So I am going to get 60 degrees. Then theta 2 is 180 by 3 into q is equal to 1. If I substitute it, I am going to get 3. So this will be 180 degrees. Then theta 3, that is equal to 180 by 3 into, if I substitute 2 here, 2 into 2, 4 plus 1, 5. So 180 into 5 by 3. So I am going to get 300 degrees. 300 degrees. So these are the angle of asymptotes which you have found out, and where these angles has to be placed. That is what we can say the location of asymptotes. So we need to find out the location of asymptotes. For that also we have used equation summation of real parts of poles. Poles in sense here open loop poles, and summation of real parts of zeros divided by p minus z. So here there are no zeros, so this term will come into the picture. So we have only 3 poles. One is at s equal to 0, and then other one is minus 5, the other one is minus 10. So that will become 0 divided by p minus z is 3 minus 0. So it is minus 15 by 3, which is equal to minus 5. Means the location is here. The location is here at exactly this pole, So you need to draw by showing this is 60 degrees one angle of asymptote. Say you need to keep with the protractor. 60 degrees you need to keep with the protractor. Then 180 degrees it is coincide with the real axis. And 300 degrees, of course, we need to keep like this. Okay, so this is how we need to. This is of course 60 degrees minus 60 degrees. So this is totally 300 degrees from the real axis, you need to go counterclockwise to represent the angle. You need to go counterclockwise to represent the 300 degrees like this. So counterclockwise. Okay, right. So once you locate this angle of asymptotes and plotting this angle of asymptotes by on the pole zero plot, that is the rule 5, rule 4 and 5 is also over now. So now coming to the rule 6, what it talks about. So that talks about the breakaway points. For any problem, you need to go in this method only. So rule 6, we don't write like this rule 6, so then we'll go step by step breakaway points. So how to find out the breakaway point? For the breakaway point, I need to write the characteristic equation, that is 1 plus characteristic equation we need to write first. Characteristic equation, that is 1 plus g of s into h of s equal to 0. So what is g of s into h of s? We told that k by s into s plus 5 into s plus 10 equal to 0. So then by using this s into s square, this implies s into s square plus 15s plus 50 plus k equal to 0. Then I can write this as s cube plus 15s square plus 50s plus k equal to 0. Then I have to write k in terms of f of s, right? That is k equal to minus s cube minus 15s square minus 50s. So dk by ds, I'll be getting 3s square plus 15s plus 50 equal to 0, because all I'm taking the minus. Of course, you'll be getting the minus. Then I'm removing the minus by sending that minus to that side, because all are minus by equating 0. So now it will become 3s square plus 5s 50 by 3 equal to 0. Then you can use this roots, finding the roots of this equation, that is x is equal to, minus b plus or minus root of b square minus 4ac by 2a. I can find out this s is equal to minus 2.113. You can use in the calculator and then find out the roots of this equation, s1 and s2. So 3s square plus 15s plus 50. So I'll be getting minus 2.113, and one more is minus 7.88. So these are the roots which I am going to find out. So substituting this in the k equation, that is this equation. So substituting in this k equation these values, I'll be getting, say for s is equal to minus 2.113, k is equal to minus of minus 2.113 whole cube minus 15 into minus 2.113 whole square minus 50 into minus 2.113. So if I substitute this equation and then find out the k value by using your calculator, then I'll be getting plus 48. So then at s is equal to minus 7.88, then k is equal to minus of minus 7.88 whole cube minus 15 into minus 7.88 whole square minus 50 into minus 7.88. So if you find out this using this equation, I'll be getting around negative value, because it will be giving a negative value. So this will not forms a, this is not a valid breakaway point, and this will become the valid breakaway point because k is positive. So this valid breakaway point has to be placed in the pole zero plot which you have drawn. So if you look at this, minus 2.11. So minus 2.1 is very near to this point. So I can show here. I cannot show exactly minus 2.113. So very near to that minus 2 I'm going to show. So this is the breakaway point, because the direction, if you draw the direction, root locus starts from the pole location. The root locus starts from pole location and ends at 0 location. So we need to show the direction of the arrows also here. direction of the arrows also, right? So we have shown the arrows, and those root locus branches comes like this in this opposite direction and breaks at this point. So I can write BP here, breakaway point. I can write breakaway point at minus 2.113, at minus 2.113. This is only the one breakaway point we have in this problem, right? So now next step is what? Identifying, whether it is going to intersect with the imaginary axis or not. So next is going to be, I'll find intersection with imaginary axis. Intersection with imaginary axis. Whether the root locus is going to intersect with the imaginary axis or not. So for that we need to have characteristic equation only. Characteristic equation only. That is 1 plus g of s into h of s equal to 0. 1 plus g of s into h of s equal to 0. That already we have done. So I using the same from the previous step. From the previous step, I got s cube plus 15 s square plus 50s plus k equal to 0. Then form the Routh array. So form the Routh array. So from the Routh array, we need to find out the row of zeros, where the for which value of k it will give the row of zeros. That is s cube here, s square, then s, then s power 0. So if you look at this two terms to be taken, and vertically downward is written, that coefficients of those s cube term and s square term, that is 1 and 15. That is 1 and 15. Then 50 and k. 50 and k. Then nothing is there, so I'll go with the writing zeros. Then s is calculated 15 into 50, 750 minus k into 1, k divided by 15. Then 15 into 0, 0. 0 minus 1, 1 into 0, 0. So 0 I'm going to get. So then s to the power of 0. This into this. Of course, if I use this, this into this minus this into this divided by this. So I'll be getting k at the s power 0. Right. So for here, if you look at this row, here I'm going to get, if there is a possibility of getting row of zeros. There is a possibility of getting row of zeros for value of k when it is equal to 750. When it is equal to 750, it is going to give the row of zeros. So equating to 0. So there is 750 minus k by 15, which is equal to 0. This implies k is equal to 750. So for k is equal to 750, it gives the row of zeros. It gives the row of zeros. Means this k will become k marginal. This k will become k marginal. So now I need to write the auxiliary equation. How to write the auxiliary equation? Just take the row above the row of zeros. Take the row above the row of zeros, that is this one. So I'm going to consider this. So now 15 into s square. How to write the auxiliary equation? So 15 into s square plus k into s to the power of 2 minus 2 s to the power of 0 it will come. So I'm not writing here. So k is here k marginal. So 15 into s square plus 750 is the auxiliary equation and equate to 0 and equate to 0. So 15 s square is equal to minus 750. So if you write s square is equal to minus 750 by 15, that I am going to get minus 50. So s is equal to, then this is equal to s, this implies s is equal to plus or minus j square root of 50. So square root of 50 from your calculator you will get plus or minus j 7.07. So this s1 comma 2 here, there are 2 points, that is plus j 7.07 and minus a 7.07. That you need to locate in this axis. Okay. So here I'll redraw this once again. I'll redraw this same pole zero plot here so that it will be easy for understanding. Now I'll redraw the same which I have drawn in the pole zero plot only. So this is about 0. This is minus 1. This is minus 2. and this is say -3, then -4, -5, -6, -7, -8, -9, up to -10 we have. Similarly here also Z, we can say 2Z or J2, 3, 4, 5, 6, and then 7. So up to we have 7, right? So I'll just show up to 7 only. J4, J5, J6, and then J7. Similarly, minus side also -J, then 2, 3, 4, 5, then 6 and 7. Say -J2, -J3, -J4, -J5, -J6, -J7. So if you have a graph, it will be easy. It will be easy to draw in the graph real axis. So this is 0, and of course this is the imaginary axis. So we have found that there is a pole at S0 and -5, -5, and -10, and also we have found that there is a sections of root locus we have found out, that is this is a part of root locus. So this is a part of root locus, and also this is a part of root locus, and the direction if I want to show, you can show like this, and here also I can show like this. Right. So now breakaway point I have located afterwards, right? -2 point somewhere here, -2.11, and angle of asymptotes, that is I can say 60 degrees. I can say here I can draw the 60 degrees. Okay, I can draw the 60 degrees. So you can take the protractor and then you can keep the angles, and also I can keep the like this. Okay, so right, so this is right. So this is what we have got. The up to the location of asymptote, that is 60 degrees, and this is say 300 degrees. From here to here is 300 degrees, and this is of course 180 degrees, and location is also -5. So now I have to show that -7.07. Of course, it is very. I can show here -7.07, and also I mean +7.07, and then -7.07 is here, and 7.07 is here. So this is up to intersection with the imaginary axis, and the next steps are we have to find out the angle of departure and angle of revival, right? So pi d is present only when there is a complex pole. Pi a is present only there is in a complex 0. So these two is not required for this problem. These two are not required for this problem. You can stop at rule 7 only. We can stop at rule 7 only. Now after stopping this, I mean identifying all those points, then now you need to draw the root locus, how it is moves as the k varies. So we got all the points. So this is the breakaway point, or we can say breakaway point. This is the breakaway point at -2.113, right? So here these two root locus breaks at this point, means breaks at this point, and one moves upward direction, the other moves downward direction. So while moving the upward direction, this branch has to move towards the infinity. It has to move towards the infinity. So here while moving towards the infinity, so here whether it is intersection, whether it is the branch or root locus is going to intersect with imaginary axis or not, because that is, yes, it is going to intersect with the imaginary axis. So we cannot draw like that. As you, I mean, say for example here, I cannot draw like this. I cannot draw like this root locus, because it has to pass through this. It has to pass through this, because this is the guideline which is approaching to infinity, So I cannot draw just parallel to this, and I cannot stop here. We have to show that root locus. We have to show that root locus is going to. Yeah. So root locus is going to pass through this point and then towards the infinity. So like this. Say for example, so here this root locus is, you can show like this. Of course, the orientation of this, because we are drawing with the free hand, so the orientation you can show like this, need not to be exactly what I'm showing here, right? Like this, but it has to pass through this point. That has to be shown here. That has to be shown here. And also the one branch is going to be moving upward direction, and we know that the root locus is symmetric about the real axis. So one branch is also moves downward. One branch moves downward and passing through this point and passing through this point and passing through this point. So this is how we need to show the root locus. So the directions also have shown, means as the k varies, this poles move from this point and then breaks at this point and then moves. One pole will move like this, passing through this point, and one pole is going to move through this and passing through this point, intersection point, towards the infinity. So this moves towards the infinity, and this moves towards infinity, and this also, third one is also moves towards the infinity. So this is what we can call it as sketch of root locus. We can call it as sketch of the root locus. From this we can say the stability of the root locus. How to study the stability of the root locus from this? See, if you look at, we need to comment on the stability. We need to look at the comment on the stability. So here I will show how to comment the stability of this system by looking at the root locus, right? So if you look at, we know that these points for the k is equal to 750 at this point, means based on the k is equal to 750, we have found that the point is intersect at s is equal to minus j 7.07 plus j 7.07. So for these values k is equal to 750, means that is a marginal value of k, means up to which the k can be varied, means from 0 to 750 it can be varied. As long as the k value from between the 0 and 750, your system is stable. Your design system is stable. Of course, if the k is 750, the system gain is 750, then the system is said to be marginally stable. Means if you're trying to increase the value of k by at least a 0.1, then it leads to the instability. So from that we can say for example, the range of values of k for which the state of system is stable, I can say for any value between 0 and 750, the system is stable. So for the range of values of k, 0 is less than k is less than 750, system is stable. So we can write system is stable. Next, at k is equal to 750, as we told that at k is 750, it is lying on the imaginary axis, we can say marginally stable system. Why it is marginally stable system? In sense, if you are trying to increase the value of k by any 0.1 also, it is going to be unstable. It's going to leads to the instability. Marginally stable system. For k is equal to 750, it is said to be marginally stable. And k is greater than 750, then we can say it is completely, the system is, mean for any value of k, if you are trying to increase this, then the poles of the system will be leads to the moving to the right hand side of the S plane. This is the S plane. So this is called right hand side. So the poles are moving in the right hand side of the S plane. So when it is coming towards the right side of the S plane, then the system will leads to the instability. So k is greater than 750, we can say it is unstable. So this is the how we can say for which value of the k, that is, as I told, that the root locus is nothing but we are going to vary the value of k, system gain k, from 0 to infinity, and we are looking at the pole movement and plotting in the S plane. That is what the root locus. So here, for which value of k the pole movement, say for example, for which value of the k pole movement is lying on the right hand side, means for any value of k is greater than 750, the pole movement will be crosses the imaginary line and moves towards the right hand side. So the system will become unstable. So you can design a system such a way that the system gain value should be within the range of 0 is less than k less than 750. Then only the system is said to be stable. So this is how you can comment on the stability of the system. K is greater than 750 means up to infinity. That is 750 less than k less than infinity. It will become unstable. The range, if I can write, if I write both are same, k is greater than 750 means up to infinity. Okay, 750 towards infinity. Okay, so that is we can say the range of values of k for the system to study the stability of the given system. So this is what we can say. This is what we can say completely. This is what we can say sketching of root locus. So this itself is, they might ask you for in your system it is 100 marks, right? So 20 marks question is, this is the 20 marks question. Study only one question will be asked, 20 marks question. It takes roughly 30 minutes, roughly 30 minutes for calculation and sketching the root locus. So parallelly, if you have a graph sheet, then it is better use the graph sheet and then plot like this. So take the x-axis and y-axis, but x-axis here is real axis and y is, always try to show y-axis on the towards the right side, rather than generally what we do is we'll plot the graph like this, 0 and this is x and this is y, like this in the xy plane. And but in the s plane, better you draw this in this direction, in this way, because it will be easy for you to show the root locus, because maximum poles will be lying on the left hand side and then very few poles will be lying on the right hand side. Okay, right. So that is why so you use the graph sheet, so that we can construct the root locus easily. So this is I have used in this problem, that is rule 1. That is rule 1 is symmetric about real axis. So how it is helpful symmetric about real axis means, so we have taken the breakaway point. At the breakaway point, we have moved the root locus like this, right? So when it is moved upward, then the other one has to move downward. So this is what we can say the symmetric about the real axis. So that is the rule 1 we used here. And then rule 2 is also we use, that is p is equal to z, or p is greater than z, or p is less than z. That case we have identified that by finding the p and by finding the z. Similarly, the rule 3, pole zero plot, initial pole zero plot we have drawn and then identified the sections of root locus. Then we have gone to the, based on the rule 2, rule 4 and rule 5 is also calculated. That is, which one? Angle of asymptotes and location of asymptotes. Then rule 6, of course, breakaway point. For any problem, we need to use the rule 6, and for any problem, you need to use the rule 7. And rule 6, we found out that there is a one valid breakaway point. And rule 7, yes, we found out that there is a, it is going to intersect with the imaginary axis. That points also located. Located by using the auxiliary equation, roots of the auxiliary equation. So we have written the auxiliary equation, equated to 0, and find the roots of that. That will be the intersection with the imaginary axis. Next, rule 7 and 7 is over. Then 8 and 9. That 8 and 9 is not required in this case because the problem itself says it is a real root. Complex roots. There are no complex roots in the g of s into h of s function. In the g of s and h of s function, numerator roots and the denominator roots, if you look at, only we have the real roots. That's why rule 8 and rule 9 is not required in this problem. So that is how we can solve the root locus. So I'll just brief about the rules which you can study till now, so that we can wind up and we'll discuss in the next class. So first, rule 1. Rule 1 is root locus is symmetric about. So we have not taken any part of this, and in numerical part we have not taken this. We have just analyzed in while sketching the root locus. We have taken this consideration, symmetric about real axis, because we have one pole moved in the upward direction, then the other pole has to move in the downward direction. So that's why it is not involved in the part of calculation, but it is required. Rule 2 is what? Finding p is greater than z or P is less than Z, or P is equal to Z, and also P is equal to Z, and how many poles are there, how many zeros are there, and where locations also, all this we found out in this rule 2. Then rule 3 is what? Pole zero plot. Pole zero plot. We can say pole zero plot, identifying sections. Identify sections of root locus. Identify sections of root locus. Okay. Then rule 4 and rule 5 depends on rule 2. Depends on rule 2. If rule 2 is P is greater than Z case and P is less than Z case, then rule 4 is used, and that is rule 4 is nothing but angle of asymptotes. Angle of asymptotes. Then rule 5 is used, location of asymptotes. Location of asymptotes. If it is not satisfied this condition, that is, if P is greater than Z and P is less than Z is not satisfied, that is P is equal to Z, then rule 4, rule 5 is not at all present in the calculation of the root locus. Sketching of the root locus. So next, rule 6. Yes, the rule 6 is compulsory for all the problems. That is, rule 6 is breakaway points. So we know that what is the procedure used for breakaway points? That is, write the characteristic equation 1 plus g of s into h of s equal to 0. Then k in terms of f of s. Then first derivative of k is going to be found out and equate to 0. Then find the roots of that equation, and after finding the roots of that equation, those roots has to be substituted in the k is equal to f of s equation. If k is positive, then that root is called as a valid breakaway point. Valid breakaway point. So finding out the breakaway points, and then rule 7 talks about the intersection with imaginary axis. Intersection with imaginary axis. So intersection with the imaginary axis, here I am going to use the Routh array. Here I am going to use the Routh array concept to find out the k marginal and also intersection points of the imaginary axis. So that is by using the Routh array only we are going to do. So you need to understand how the Routh array concept, which I have discussed in the previous module. And in this module only. Rule 8 is also, these two are dependents once again. These two also depends on the same rule 2. So rule 2, okay, rule 8 and rule 9. Rule 8 and rule 9. Yeah. So I'll write rule 8. Rule 8 is angle of departure. Angle of departure. Rule 9 is angle of arrival. Angle of arrival. That is, and pi d is equal to 180 minus pi, and pi a is equal to 180 plus pi. Okay. So when we are going to use this, so rule 2, if we are finding the p's, after finding this number of poles and number of zeros, then we are finding the locations. Locations are nothing but whether it is a complex roots or real roots. Real roots are complex roots in this case. So if there is a complex roots here, then this will be used. Complex roots are complex pole if you have. If you have a complex pole, that is in the denominator roots are complex roots. If the denominator roots are complex roots, then we can say angle of departure can be used. If the complex 0 is present in the system, then I am going to use the rule 9. I am going to use the rule 9, that is angle of arrival. So here these two rules also depends on the rule 2. 4, 5 is also depends on the rule 2. So for remaining 1, 2, 3, 6 and 7 is compulsory for all the problems. So if you understand this complete overview of this sketching of root locus rules, then it will be easy for you for any problem. If you give the same procedure can be applied in sketching the root locus, right? So we'll stop today.